When we last left, if I remember correctly, we were going through the instructions of the next assignment, and I think we got down to you have to support batch and mini-batch gradient descent, and I wanted you to add support for momentum, and we were talking about what the heck momentum is, and that's basically when we ended. So, continuing on. Here's the idea of momentum. It's basically remember a little bit of the last gradient and keep it going. And as long as that memory contains just the last gradient, do you see how it also contains a fraction of the piece of the gradient that was before it? Let me illustrate that graphically. Let's suppose you take a cup out of the ocean. Let's see. Let's do it this way. You have two cups, and this cup is full of water, and this cup is full of something that contrasts with water. Let's go with P. Okay, so what am I going to do here? I'm going to pour this cup into that cup. Come on, tip. Can't quite tip my program very easily. There's a rotate function, but it's a pain to use. So just pretend I pour, how much of it? Let's just say I start with 100% P and then I fill it up. I'm going to retain how much? 50% of it? Okay, let's suppose I dump 50% of this out, so now 50% of the P is gone. And then I pour water into it and I mix it in and it goes, fills it up, goes to there. Now it's 50% P, 50% not P. And of course we all know what's really going to happen is it's going to distribute and it's going to look kind of like this. Dirty water, right? But suppose now we only we dump 50% of that out and we fill it up again with nice fresh clean water because this is a refilling cup. Here, let's draw a faucet too. Okay, now what's going to happen to this? Well, it's a little bit cleaner. And then we dump 50% of it out, we fill up that 50% and repeat, and we keep on doing this over and over and over and over. Will we ever get all the P out? And why did we pee in our cup anyway? I don't know. That's not the point. I just wanted some attention, and I got it, didn't I? Okay. Practically, will you get the P out? Yeah. How long? How many times would you have to do it before you drink it?
Never.
Never? You would never drink from a cup that had been peed in. Okay. In real life, how many times do you actually have to do it? Let's see. If I remember correctly from my chemistry from high school, there's 1 mole of atoms in a gram of hydrogen. So what's that? 6.022 times 10 to the 23rd. That's 1 mole. So let's say that's 1 gram of hydrogen. Wait, that's how many? Is that how many molecules of water there are in a gram? No, I think it's going to be like it's about 18. That many molecules would have 18 grams of water. Okay. So how many grams do you think are in this cup of water? Let's say 100. I don't have any idea how many. Oh, wait a minute. I have a Google. How many grams in a cup of water? That's not Google. That's DuckDuckGo. Google would give me a real answer. Okay, 236. We're going to say there's about that many atoms in this cup of water. Therefore, presumably, I want to see how many times I have to divide it by 2 before I start getting quantum effects, and then I'm just going to wipe out the last few atoms, because you're not going to divide water molecules in half, right? So log, if I take the logarithm of that divided by the log of 2, so I'm taking the log base 2 of that 86 times. Apparently, if you dump the cup halfway out 86 times and fill the other half up with water, now you're starting to get to the point where, unless you're splitting atoms of P, you don't have atoms, molecules of P. I don't even know what that is. You're going to start running out of them. So probably by about 100 times, you could say with pretty darn certainty, there's nothing in there that wasn't. I mean, you're going to have more impurities in your tap water than you probably would have in that cup that was previously filled with P after about 100 times of cutting it in half. Sound reasonable? Okay. Why did I do this? And what does that have to do with machine learning? I don't know either. Okay, I do know. It has to do with this thing. What is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus ... on to infinity?
1. Or actually,
it's actually 2. Because I said 1 when I started. Yeah. Okay. It is 2. And it's actually not 2 until I get to infinity, but it gets so darn close to 2 after just a few iterations that nobody cares anymore. Basically, that thing is equal to 2. What's 1 plus 90% of 1 plus 90% of 90% of 1 plus 90% of that plus 90% of that plus 90% of that plus 90%, and so on? The equation's right there. Come on, do it. Fine, I'll do it. All right. It's 1 over 1 minus 0.9, which is 10. So apparently, if we, let's see, it doesn't have anything to do with the water analogy, does it? Let's get rid of that water analogy. That was a bad appeal to unrefined senses just to get attention. But according to this, 1 plus 0.9 plus 0.9 squared plus 0.9 to the 3rd power plus 0.9 to the 4th power plus 0.9 to the 5th power is 10. Do you get what this equation does? Basically, if you take any number, whatever that number happens to be, and raise it to successive powers from where the powers of the integer numbers from 0 all the way up to infinity, then this computes the number for you. And as long as m is reasonably smaller than 1, meaning if m is close to 0 or 0.5 or something like that, it's going to take a pretty small number of iterations before it converges darn close to that value, right? And if m were 0.99999, then it would probably take maybe a few thousand, but eventually it would get right to the number that this thing computes. Okay. When we do gradient descent, imagine that we were going like that direction, then that direction, then there, then there, then there, then there, then there, and we end up at our goal. If we were to average these gradient directions, this plus that on average would be more like that. Okay, let's do the smooth version. So at first we don't have anything else except the one step, right? Second time we have kind of 2 steps contributing to our accumulated step. I guess this plus that is going to be more of this direction, and it's a little bigger because we've got 2 of them added up. Hey, look, I made a star. Okay. What's the third one? The third one's now going that way. So if I go this way again plus that way a little more, now I'm kind of going this way. Then the fourth one goes up this way. So more of this plus some of that way is going to be a little bit less. We're now slowing down. Then the next step goes like that. So this thing's going to go that way next. Now we've kind of overshot our goal. Oh wait, there's a big mistake I'm making. Anybody know what the mistake is? I was assuming it was going to compute the exact same gradient directions each time, but it wouldn't because I'm in different places now each time. And so the gradient from these new places is going to be different than it was in the original places. So what I just did, bad example, forget about that. But did you see what I was doing? I was kind of trying to show what a path would look like if I had a bunch of momentum. And well, the blue one's smoother. It doesn't quite hit the same point, but it kind of gets near there. And it would eventually probably get there if we had added it up with momentum. A question we can ask when doing the momentum is this. Remember, there's a whole bunch of components added together inside of this gradient, right? Meaning, if we were to go in here, we could ask the question, what percentage of this gradient step is p? By which I mean, we could say that probably, let's suppose our momentum was 50%. In that case, at least 50% of it is the most recent gradient that we just saw, right? And then about 25% of it is going to be the gradient that we saw just before that, the one that came from a point 2 time steps ago. And then half of that amount is going to be from the gradient we saw just before that. And then half of that amount is going to be from the gradient we saw just before that. And half of that amount is going to be from the gradient we saw just before that. And at some point, we're actually summing together more gradient points than have actually occurred since the beginning of time when this step began, because there weren't infinity steps to get to this point, right? So this equation doesn't exactly tell you how many gradients have contributed to the, or how many stochastic patterns have contributed to your current gradient, but it does give you what it would be if you had taken an infinite number of steps. The reason I've produced this little equation here, or the reason I've put this little equation here, I didn't produce this, somebody smarter than I invented it. But one could ask the question, hey, isn't momentum a lot like batch gradient descent? Do you see why it's similar? Because when you do momentum, your gradient is actually the accumulation of a whole bunch of pattern presentations all stuck together to compute one gradient. And when you do a mini batch, you're actually visiting a whole bunch of different patterns and computing their gradients and adding them together to compute the gradient. Therefore, they're sort of doing the same thing. So if we wanted to compare them, I'd kind of like to know what is the sum total number of pattern presentations in here, given that it's 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. So if that were the case, it was 1 plus 1/2 plus 1/4, meaning my momentum was 0.5, then the answer is 2. This is kind of equivalent to a mini batch size of 2. Do you see that? It's not really equivalent because this second one, there's 1 and then 2, that second one is really composed of a whole bunch of pieces of a bunch of pattern presentations. But if we say that together they're all acting as one other presentation, because that's how much weight they carry in that first half, then I can say that this momentum is sort of effectively comparable to a batch size of 2. So I'm claiming momentum of 0.5 is related to a mini batch size of 2 because of this equation. Okay. Only reason I put that there is use this equation to compute the effective mini batch size And when I say effective, I'm doing air quotes there. I'm saying whatever this number says is the number of pattern presentations that have contributed to produce the current gradient at where you are. We're going to call that the effective mini batch size. Effective mini batch size. If that makes sense. Yes?
Well, the first part, you're saying that all the pieces of the gradient that are coming into momentum are just acting as one, then wouldn't a momentum of any size still just be a mini batch too? Because you have the stuff that you're computing plus the previous stuff.
Actually, no. And here's why. Because it's not cutting, the weighting is not, let's do an example. Let's suppose my momentum is 0.9. By m, don't think slope, think momentum now, because I can't type a Greek mu, which they usually use for momentum because it has a m sound. Okay, I could just write a mu here. There. There. Momentum equals 0.9. What that means is at the end of each, or rather at the beginning, just before you compute your gradient, instead of doing a gradient.fill 0.0, you're going to do a gradient times equals 0.9 because we're having 90% momentum. What that means is we're really dumping out only 10% of the gradient we had before, and then we're going to add to it whatever gradient you compute from forward propagate, back propagate, update gradient. So. Excellent question. I don't know. I've seen numbers as high as 0.9, and I've used 0.9 and got it and had it effectively work with some data sets. If you go up to 0.9, though, in fact, actually, that's another reason this is a useful equation to know. If you go up to 0.9, then your step size is going to be about 10 times your intended step size. At least the largest it'll ever get is taking about 10 times as much step as you meant to. Does that make sense? So in order to use gradient momentum effectively, you sort of have to, when you tune up the momentum, you have to tone down your step size. And I guess you could use this equation with the momentum to scale your step size accordingly. So in answer to your question, I've seen numbers as high as 0.9. 0.8 or so is probably more common. It usually works with 0.8. If you go lower than that, then it almost certainly works. But if you go too much lower than that, what's the point? Because you're not averaging together very many patterns. So I guess momentum probably ranges between 0.5 and 0.8 in the wild. But it really comes down to people will try it and tune it, and whatever works is the correct answer.